Good morning, everyone. This is M. Pavan from CSC Data Science Group from IRE College, first year. Now, I am here to explain you one concept from physics. In this, my concept is concept of Kirchhoff's voltage law and problems on it. Here, in this, we will know what is Kirchhoff law and how it is useful for us, and we will see some of the problems on it. Means we will see how the problems to be solved using the Kirchhoff law. Next, Kirchhoff's voltage law means understanding loops in a circuit. Means we use this law in circuits. The Kirchhoff's current law and Kirchhoff's voltage law are the basis for analysis of lumping parameter circuits. These laws, together with the voltage current characteristics of the circuit elements in the system, provide us with the ability to perform a systematic analysis of any electrical network. Now, this section presents Kirchhoff voltage law. Means in Kirchhoff laws, we have two laws: Kirchhoff current law and Kirchhoff voltage law. From that, these are the two together will with the current voltage characteristics of the circuit elements in the system. Provide us the ability to perform a systematic analysis of an electrical network. This section presents us. Now we are going to see what is Kirchhoff voltage law and how it is going to useful for us in the circuit for finding the voltage. This is the first and foremost thing we need to learn in this Kirchhoff voltage law. Then we can see what are the problems on it and how we are going to solve those problems. Next, we will move to the next slide to learn this more. KVL means Kirchhoff voltage law depends upon the concept of a loop. A loop is any closed path around the circuit which encounters no node more than once. Essentially, to create a loop, start at any node in the circuit and trace a path through the circuit until you get back to your original node. KVL depends upon the concept of a loop. A loop is any closed path through the circuit which encounters no node more than once. Essentially, to create a loop, start at any node in the circuit, trace a path through the circuit until you get back to your original node. KVL depends upon the concept of a loop. A loop is any closed path through the circuit which encounters no node more than once. Essentially, to create a loop, start at any node in the circuit and trace a path through the circuit until you get back to your original node. KVL depends upon the concept of a loop. A loop is any closed path through the circuit which encounters no node more than once. Essentially, to create a loop, start at any node in the circuit and trace a path through the circuit until you get back to your original node. The concept of a loop is probably most readable explained through a few examples which we have provided below. Okay, we will see how the KCL goes on. Signs to be given to voltage drops means when we are considering a loop, we need to specify with the signs. Otherwise, we will be in problem. So when current flows through a resistance, there is a voltage drop IR. If we go in the direction of flow of current, a negative sign should be given to the voltage drop, falls in potential, as current flows from higher potential to lower potential. If we go in the direction of the flow of current, a negative sign should be given to the voltage drop, fail in potential, as current flows from higher potential to lower potential. However, if we go in the opposite direction to the flow of current, a positive sign should be given to the voltage drop, rise in potential. Means the signs to be given to voltage drop when current flows through a resistance, there will be some resistance drop. Then if we go through the direction of the current, a negative sign should be given to the voltage drop as current flows from higher potential to lower potential. when it is going in the opposite direction of the current, a positive sign should be given to the voltage drop. As it at that time it will go to higher potential to lower potential, but we are moving the opposite direction, means lower potential to higher potential. Then we can give the positive sign to it. This is the sign conventions which we use in the Kirchhoff voltage law based on the direction which the flow of current. If we going in the direction in the flow of current are opposite to the flow of current. This is the two basic things. Next from this, steps to involve currents in Kirchhoff voltage law means there are some following steps to be followed to find the Kirchhoff voltage law. To use the Kirchhoff voltage law, we need some steps, and that should be followed at at appropriate timings. Without that, we can't be find the how the Kirchhoff law is going to allow. This is the first and foremost thing we need to follow this. Mark the direction of flow of current in various branches in the circuit according to Kirchhoff current law. Means we need to first find the how the flow of current goes on, because we need to go in the direction of current flow or in the opposite direction of current flow. To know whether the opposite or along the direction of current, we need to mark the direction of current flow in various branches in the circuit. For that, we need to use the Kirchhoff current law. Current law is mostly helpful for us to choose the direction of the flow of current. Then choose as many number of closed circuits as the number of unknown quantities. Choose as many number of closed circuits means in a circuit we can find some closed circuits in them. So choose as many members of closed circuits as the number of unknown quantities. Find the algebraic sum of voltage drops and EMFs in that current and put the sum equal to 0. Now, as we find the closed path, now we need to see the direction, are we flowing direction going to flow the current or opposite to current, and we need to find the algebraic sum of voltage drops and EMFs in that circuit and put their sum equal to 0. Then we must equate them to the 0. After solving the problem, if the calculated value of the current has a positive sign, it indicates that the direction assumed is correct. Means what we are assuming the flow of current direction will be right. If the problem after solving the calculated value of the current has the positive sign, means then the direction we assumed is correct. If it has a negative sign, it means that the actual direction of flow of current is opposite to that of assumed direction. Means we need to think in the opposite direction of that. Means now we are thinking that it is in the when it is came in the positive value, then we will think that it is in the straight position, direction of the same position. But if it has negative sign, it means that the actual direction of flow of current is opposite to that of assumed direction. This is the first and foremost thing we need to know about this. Then only we can find the exact values. If it has the negative sign, it means that the actual direction of flow of current is opposite to that of the assumed direction. Next, we will see example. Here we are having one example. Means this is what we are going to learn. Here we are having the loops. This is one loop, this is one loop, and this is other loop. For all these loop, this is the first and foremost. This is a whole loop, and this is one of the loop, and this is one of the loop, and they having in middle three of the loops. For each loop, we can apply KVL to find the current in which direction it is passing and which direction it is leaving, and everything what we want to know at each and every point we can find by using KVL and KCL, Kirchhoff voltage law and Kirchhoff current law. For that, we need to find the direction of flow of current, and we need to think about the loops, how it is going. We need to understand how the direction it goes on. We need to find whether it's going in this direction or opposite to that what we are assuming, and we need to be specific in these things. Otherwise, we won't be able to do what we want. Next, Kirchhoff voltage law, commonly abbreviated as KVL. What I said before, it states that what the statement of this thing is the algebraic sum of all voltage differences around any closed loop is 0. Means what I am trying to say is the what we are seeing in the loops in the circuit, the algebraic sum of all the voltages in any closed loop, whether it is a whole loop or it is in only one loop or it is in a consists of how many members, we no need to specify them how many points or how many things are there, but in any closed loop the algebraic sum of all voltage differences around any closed loop is zero. An alternative statement of this law is, means that the statement, we have an alternate statement for this is the sum of the voltage rises around a closed loop must equal the sum of the voltage drops around the loop. Means the sum of the voltage rises around a closed loop must equal the sum of the voltage drops around the loop. The sum of the voltage arises around a closed loop must equal the sum of the voltage drops around the loop. Or even when going around a loop, you have to get back to the same voltage you started with. Means when we are taking in a loop, when we are going to throw in a loop, you have to get back to the same voltage you started with. Means what you are at the starting position, what you are having, you need to be same with the ending position also. There nothing to be changed with those things. That is the first and foremost thing we need to understand in these things. Means the sum of the voltage arises in any closed loop must be equal to the sum of the voltage drops. Means what the voltage rises must be equal to the voltage drops also. That is the thing which should be followed in Kirchhoff voltage law. When we going around a loop, then we can find that you have to get back to the same voltage you started with. When it is raising, then it is coming voltage drop. Those things should be equal. Then only the Kirchhoff voltage law will work out on this. Then we are having some note here. Voltage polarities in the loop are based on assumed polarities of the voltage differences in the loop. Means we are having voltage polarities in any loop. In when we are considering one loop, then the voltage polarities in the loop are based on assumed polarities of the voltage differences. Assumed polarities of the voltage differences in the loop. As long as the assumed directions of the voltages are consistent from loop to loop, the final result of the analysis will reflect the actual voltage polarities in the circuit. Voltage polarities in the loop are based on assumed polarities of the voltage differences in the loop. Means the assumed polarities of the voltage differences in the loop, as long as the assumed directions of the voltages are consistent from loop to loop, the final result of the analysis will reflect the actual voltage polarities in the circuit. As long as the assumed directions of the voltages are consist from loop to loop, the final result of the analysis will reflect the actual voltage polarities in the circuit. Then the one of the important point in Kirchhoff voltage law is, finally Kirchhoff voltage law states that the sum of the voltages difference allowed any closed loop is circuit must be zero. Means I am stating this from the starting that the Kirchhoff voltage law finally says that the sum of the voltage differences, means voltage drop or voltage gain, voltage rises or anything in one closed loop in a circuit must be zero. A loop in a circuit in any path which ends at the same point where it started. Means in a loop means it is a circular loop. A loop in a circuit at any path means it is starting from another path or different kind of paths. A loop in a circuit in any path which ends at the same point at which it starts. Means from the starting and the ending point of the loop must be the same. Finally, this is the Kirchhoff what it's trying to say as is a loop in a circuit is any path which ends at the same point at which it starts. That's the final thing it wants to tell to us. Then we are having the conclusion of this. In this conclusion also, we are trying to tell you the same. What the Kirchhoff voltage law or KVL or whatever it is, what it is trying to say is, it states that in any closed loop network, in any circuit, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop. Means the voltage arises and voltage drops within the loop. The voltage drop around the loop is equal to the sum of the voltage drops within the same loop, which is also equals to 0. Means the in any closed circuit, when we are having a circuit, we have so many things, we have so many loops. In one circuit we can find so many loops. Approximately we can find more than 3 loops we can find, or more than 2 loops we can find in any loop, whether it is a fully closed loop or in a loop inside one loop or any loop. If we applied the KVL in any loop, in any closed loop network, the voltage, the total voltage around the closed loop, around the loop, is equal to the sum of all the voltage drops within the same loop, is equal to the sum of all the voltage drops within the same loop, which is also equal to 0. In other words, the algebraic sum of all voltages within the loop must be equal to 0, which is also equal to 0. In other words, the algebraic sum of all voltages within the loop must be equal to 0. In this, what it is going to explain you is the sum of all the voltages in any closed loop, in any circuit, whether it is a negative sign when we are applying in the direction of the flow of current or opposite to the direction of flow of current, anything with what we are signs are using, when we write an equation with this KVL, that must be equal to 0 only. Then we will find the values, voltage drops and voltage rises. Those things also must be equal. Those things must be equal and should be equal. There will be nothing to change in with them. That the Kirchhoff voltage law says that in any closed loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop, which is also equal to 0. In other words, the algebraic sum of all voltages drops or voltage rises within the any closed loop or path must be equal to 0. There will be nothing to change with these things. Those won't be nothing or anything, nothing to be changed. That's the only thing I can try. I am trying to tell you is this. This is the only thing. So I feel that everyone understand what I'm trying to say, tell, and I feel everyone understand what is Kirchhoff voltage law and how it is used in our circuits. And thank you for giving me this golden opportunity, for being me, for here with you. And thank you all. Thank you for being with you, and thank you for giving me wonderful opportunity. Thank you all.